Okay, so in the last class, we had discussed about the basics of FM, and we also got to know how to generate a narrow band and wideband FM. Now we shall try to see how we can demodulate the FM signal. So this block was shown in the previous video also, where you have a slope circuit as well as the envelope detector. So this is basically FM discrimination method. A slope circuit is nothing but a differentiator basically, which can also be called as a LC circuit, a tuned circuit. So we shall see the circuit diagram of it. So this is how the circuit diagram of a slope detector will look like. You apply the FM input. There is basically a transformer setup there. Now it depends on what frequency this particular LC circuit is tuned to, because based on that, the circuit is going to operate. Supposingly, if I tune this circuit to FC, let's say, FC becomes a center frequency, and this LC circuit would behave like a simple resonant circuit. And all of us know how the response of the LC circuit looks like. You can see this particular waveform, where you can see, if at all the circuit is tuned to FC, this frequency will be equal to FC. And where would FC plus delta would appear? FC plus delta F would appear somewhere here. FC minus delta will appear somewhere here. Now, will this serve the purpose? Because we say that the frequency will get tuned or changed to FC plus delta if the modulating signal reaches the positive peak value, and FC minus delta if it reaches negative peak value. This is what we say, isn't it? So, but if at all the LC circuit gets tuned to FC, what happens is, as and when the input is applied, that is the modulated signal is applied, the change in the frequency will make the amplitude to basically get reduced, isn't it? And similarly, the reduction in the modulating voltage will see the reduction in the frequency, which again makes this circuit to give an output where the amplitude reduces. So for both FC plus delta and FC minus delta, the amplitude is going to reduce, which is not a good thing. So that is why the circuit is always tuned to what is FC plus delta. So if you are tuning it to FC plus delta, what happens? When the frequency arrives at this circuit, slope detector, as the circuit is already tuned to FC plus delta, if at all you are starting the waveform from FC, which is zero modulating signal, obviously the voltage what appears at the output will have a voltage which is in between FC plus delta and FC minus delta. So as and when the frequency increases towards FC plus delta, what happens? The amplitude increases. This is what we expect. As and when the frequency increases, modulating signal voltage should also be raising. So this is kind of reverse process of what we did in the frequency modulation block. So when basically FC comes back to FC minus delta, the amplitude reduces because it is at this particular point, FC minus delta. So this is FC plus delta. This will be FC point. That will be FC minus delta. So what you see is a linear curve which shows an increase in the voltage as well as the reduction in the voltage. So this is what we are expecting. So this is how basically this circuit is going to behave. And once this LC circuit operation is over, that is at this point, if you observe at this point, after this operation, what you see is basically an envelope detector. This envelope detector is nothing but a demodulation circuit. Now if you come back to this, what you observe at this point is a waveform which is amplitude modulated kind of thing, isn't it? So the amplitude of the carrier, anyways the frequency is changing there, but the amplitude is also varying because of the slope detector operation. Now this kind of input is what is used in the envelope detector. So envelope detector will basically take care of the actual demodulation process which has to happen, and we'll be able to get back our message signal. Now this block diagram basically speaks about a balanced frequency discrimination. So this is something like a two-fold circuit which was earlier discussed for the slope detection. Okay, why do we require it? When you observe the frequency response, we have written a very linear response at this point. If you see the slope of these two, on the either side of FC plus delta, the response looks more linear. But in the practical scenario, this is not the case. You will have a very non-linear response as far as the LC circuit is concerned. So when there is a non-linearity existing, obviously the waveform what we get at the output of the slope detector will not be actually the modulated envelope. So in that case, we will lose out the information. So we have to safeguard the information, and for that reason we go for a two-fold network like this, where we use two slope detectors. One, the above one will be tuned to Fc plus delta, the below one will be tuned to Fc minus delta. So you will have two different tuning circuits to basically fetch out the signal properly. So the process will remain the same, the operation of the circuit will remain same, but the advantage of going for two-fold is the non-linearity reduces. So this is how we can take care of it. And this will be the actual circuit of it. So what you observe is the same circuit but tuning to different frequencies as such. And this is the frequency response of it. So you can observe what is happening at Fc plus delta and Fc minus delta. The same response, but we have tilted the response because Fc minus delta is appearing at the bottom. Okay. What are the advantages of the circuit? The circuit is more simpler. The circuit is more efficient than simple slope detector. It has better linearity than the simple slope detector. The major disadvantage is it is always difficult to tune, since the three tuned circuits are to be tuned at different frequencies. Input is tuned at Fc, and then you have Fc plus delta for the above one, Fc minus delta for the below one. Amplitude limiting is not provided in this case. So this is also one more important disadvantage. Moving on to the next kind of FM detection, we've got what is called as a zero crossing detector. So this detector basically exploits the property that the instantaneous frequency of an FM wave is proportional to delta t, which is the time difference between adjacent the zero crossings of the FM wave. T is chosen in such a way that the zero crossing detector operates on the principle that the instantaneous frequency of an FM wave is approximately given by Fi, which is equal to 1 over 2 delta t. So probably we'll take an example here. So this waveform is what is written. We'll take a window capital T, and capital T value should be in such a way that it should be larger in comparison to Tc, which is nothing but 1 over Fc, that's the carrier frequency or the period of the carrier signal. So this capital T value should be far greater compared to Tc, and at the same time it should be very small in comparison with Tm. So it should not be occupying the entire modulating signal period. It should be very small. So the window should be aptly selected. And we define one thing which is called as delta t, which is the spacing between the two zero crossings, adjacent zero crossings. So based on that, we can define what is called Fi, which is equal to 1 over 2 delta t. So this becomes obvious. You try to take the four adjacent zero crossings, number 1, 2, 3 and 4. You can see that. If you see within the duration capital T, you can see 6 number of zero crossings happening, starting from the first one, second, third, fourth, fifth and sixth. So 6 zero crossings are happening, or you can just say it is only 1, 2, 3, 4 zero crossings. It all depends on how we our perspective. So based on that, you can define what is Fi equal to. Now what do I get out of Fi is, we'll be able to understand that Fi is basically tracking the change in the frequency, that in turn will give me the change in the amplitude of the modulating signal. How we shall try to see. So when I give this to a when the FM signal is given to this zero crossing detector, which contains within it a limiter, a pulse generator as well as an integrator, which is nothing but a low pass filter, what happens? A limiter, or it's also called as a zero crossing detector, it tries to see how many zero crossings have happened. Pulse generator will generate a pulse for every rising edge in the zero crossing. So how will the output look like? Let me show the output, how it looks like after the limiter. So after the limiter, you can just say the waveform is going to look like this. Okay, I've just shown the part of the waveform where there is an decrease in the frequency, which is for the negative period. So if you observe the rising edge of every pulse here, this pulse generator will generate a pulse of a very short duration like this, which is constant pulse width for every rising edge. So this pulse generator is nothing but a monostable multivibrator, which will give out the pulses. So you can get a pulse like this. And remember, the width of all these pulses will be constant. Then it reads out how many number of pulses you get within the time period capital T. And that will decide what is the amplitude of the modulating signal. So let us say at first instance, let me erase this all. At first instance, you will get some 2 number of pulses, then it goes up to 4, then it goes up to 6, and then comes back to 4, then 2, then 1, then nothing. So what is happening here? the increase in the number of pulses what you get means that there is too many number of zero crossings happening. So this part is basically indicating the positive part of the modulating signal. The other part indicates the negative part of the modulating signal. So based on the number of zero crossings, you can judge whether the amplitude is increasing or decreasing as far as the modulating signal is concerned. So this is what is going to happen in a zero crossing detector. Okay, so that was all about the zero crossings. Now we shall try to understand what is FM stereo multiplexing, which is one of the major application of a FM signal. So what is FM stereo multiplexing? FM stereo multiplexing is basically multiplexing two different signals, okay, which are coming from two different sources. For example, if I say we are playing a music will contain many instruments. Let us say for the time being there are two things. One is a guitar being played. At the same time, there is a vocalist. So these two people are giving out the source signal. So ML of 1 or ML what is written here is basically the voice of the vocalist. MR is nothing but the music which is coming out of the guitar. So now these two should be sent together. Now what we can do is we can have a single channel and try to transmit it, but we'll lose out the sensitivity, or I can say the quality of the music if they are just combined together without any proper means. So the best way of doing it is what is called multiplexing. So that is what is called as a stereo multiplexing. You'll be able to basically hear the stereo effect when you do the multiplexing of signals in this way. So this block diagram is a very standard block diagram of a stereo multiplexing. We'll be able to understand when we start writing the equations for all these things. So what happens at the above is, let me put that here. You have ML and MR getting added. You have ML and MR getting subtracted. We use a product modulator. Now the other input given to the product modulator is coming from a frequency doubler, which doubles the frequency. A cos 2 pi FCT now becomes cos 4 pi FCT. Now that is getting multiplied with ML minus MR. So what you have at the output of product modulator is this: ML minus MR whole multiplied by cos of 2 omega CT. This is what you get. Okay. Now this is nothing but a kind of DSBSC signal. So all the three signals, number one is ML plus MR, number two is the output of the product modulator, which is the equation that I've written here, and third one is basically the cos 2 pi FCT where with a amplitude multiplier K. All the three signals gets added up, and finally what you get is some M of T. So that signal is frequency modulated. So we are frequency modulating that particular signal and we'll be transmitting it. Clear? So this is about the frequency modulation part. Now we shall see how the frequency demultiplexing is going to happen. A frequency demultiplexer is this. So we have a FM detector. It does the frequency demodulation as such. Further to it, we have got three different channels. One is the band pass baseband low pass filter. Second one is a band pass filter with a frequency tuned to FC, 2FC. Third one is a narrow band filter tuned to FC value. So cos 2 pi FCT is derived out of the narrow band pass filter. A baseband filter will only give you the signal. Just let me have the pen. Okay. Okay. Okay, fine. So this will contain ML plus MR within it. Okay. Now this part is basically trying to squeeze out the information which was done in the second channel here. Let me show that. This is what we had, ML minus MR. So this information is what we want again back after this. So that is what you get after you perform this. But in the process, this block is also used. So this gives you the carrier frequency. We double it. We give it to the product multiplier here, the product modulator block, which is nothing but a DSP as a demodulator. And I use a baseband filter to only get this much. Now this part is identical to what we had here. See here, same thing. So when you perform this operation, what you get back is ML as well as MR. So I'll be able to get back the actual two signals which were sent from the other side. So I can perform it using this frequency modulation. So I multiplex it, send the signal through the frequency modulator, after the frequency modulation, receive it, perform FM demodulation, and then you basically perform this so that you can get back your individual signals. So this is about the stereo multiplexing. Is there any questions on this? This has a lot of applications as such. Too many applications are there on this. So we can better understand when we write equations at every stage. So equations will clarify all our questions relevant to all these things. Okay. Yeah. So we shall now discuss about the next kind of frequency demodulation, which is the phase locked loop. We shall try to understand it. Okay.